I'm Curtis Brown, and I am from Texas Instruments, and I'm here with my friend John Urschel, and we are recording some smart space videos. And this is the last in our series of geometry videos, and this time we're really going to look at the connection between algebra and geometry. We're going to explore a couple of things. We're going to explore maybe the Pythagorean theorem, and then we're also going to spend a little bit of time exploring slope and kind of the connection between what we've explored in these last videos of congruence and similarity and how that connects to slope of perpendicular and parallel lines. So John, you ready to take it away?
Yeah, I'm ready to go. So this last one is really all about sort of tying geometry and algebra together in some sense. And this is really what all these lectures have sort of been doing when we think about congruence in terms of rigid transformations and similarity in terms of those rigid transformations plus dilation. And so this time, let's dig into some concepts we know and see how we can relate algebra and geometry. We're going to review things like distance, Pythagorean theorem. We're going to think about slope in terms of triangles. And we're going to look at some properties of parallel and perpendicular lines. Curtis, how's that sound?
I think that sounds awesome. Let's do it.
Okay, first of all, review. How do we measure distance? If you remember, the distance formula for 2 points, x1, y1, and x2, y2 in the plane is just the difference between x1 minus x2 squared plus y1 minus y2 squared, and we take the square root of the whole thing. Right. So you'll remember this from our first session, and also this is something I hope you guys remember. And I hope you guys also remember the Pythagorean theorem for right triangles. It says that if triangle ABC is a right triangle with some hypotenuse length, let's say little c, and side lengths little a and little b, then the Pythagorean theorem just says that little a squared plus little b squared equals little c squared.
Right.
And this is something we've already touched on a little bit in the first session, but I want to formally talk about how these two things are sort of saying the same thing, how we can think about the Pythagorean theorem in terms of the distance formula, and sort of think about the distance formula in terms of the Pythagorean theorem. Nice. So for instance, on this picture I have a triangle, this right triangle that I just showed you. And let's suppose my point A is at the origin.
Okay.
Our point C is length B away from the origin to the right. So we know its coordinates are B0.
All right.
And my point capital B, we know it's A units up from capital C. So we know its coordinates are little b and little a. So we've taken a right triangle with side lengths A, B, and C, and now we've mapped them onto the plane with specific points. And the cool thing you're going to notice is if we look at the distance between point A and point B, which is just the length of the hypotenuse of our triangle, when we use the distance formula, what we get is that this length is the square root of a squared plus b squared.
Nice. Okay.
And so the distance formula is actually the same as the Pythagorean theorem, because when you square both of those sides, you just get out that c squared equals a squared plus b
squared plus b squared. Yeah.
And so, for instance, let's move over to the overhead, and let's take a look at this triangle from session 1, this 3, 4, 5 triangle. And now let's label these points. So let's call this point A. Let's call this point B. And let's call this point C. Okay?
Yep.
And now, why don't we try to look at the lengths of all these different segments? So we know that AC, the length of this segment, is 3. The length of BC is 4. And by the Pythagorean theorem, 3 squared plus 4 squared equals...
Was that 9? 925.
Like AB squared.
Yeah.
This is 9, 16.
So AB squared is 25.
And so if we take the square root of both sides,
So if we, yep, root 25 is same as the root of AB squared.
so we get that the length of AB
So the length of AB, segment AB, is in fact 5. All right.
is in fact 5, and this is the same value you would get if instead of doing this, we looked at the distance between point A and B using the distance formula.
Okay. Yeah, let's check that.
A is at -1, -1. And point
Right.
B is at 2, 3.
Okay. So applying the distance formula, what does that look like?
Square root of -1 minus 2 squared plus -1 minus 3 squared.
-1 minus 2 is, I guess, 3 squared.
-3.
Or I guess -3 squared.
Plus
And -4 squared.
squared. -3 squared is 9. -4 squared is 16.
Nice.
So what we get is the square root of 25, which equals 5. And so you can see how the Pythagorean theorem and the distance formula are just two different ways of thinking about the same thing. One is a geometric way of thinking about it, and the other is a sort of coordinate-based, more algebraic way.
Yeah, I like it. This is really good.
Yeah, so this is sort of just tying in these things we know and connecting them and seeing how this is all related. So we've looked at the Pythagorean theorem and the distance formula. Now why don't we talk about lines and their slope? So the slope of a line is the ratio of the change in the y-coordinate and the change in the x-coordinate between any 2 points on this line. And so suppose we have 2 points on a line, x1, y1, and x2, y2. The slope of that line is just y2 minus y1 divided by x2 minus x1. And you might remember this as rise over run.
Yeah, definitely. Like the change in y divided by the change in x. You might have even seen it as written as the delta y over the delta x, right? I mean, there's a lot of ways you can certainly write and talk about this idea of slope.
Exactly. And now I want to talk about this idea in a way that you might not have seen before. I want to think about slope, something that, you know, seems very algebraic. I want to think about it geometrically.
Okay.
So suppose we have some line L, and we have 2 points on it. We can form a right triangle.
Oh, sure.
Adding a third point. So if A is, let's say, the point x1, y1, and B is the point x2, y2, why don't we just add the point C, which is x2, y1, and you can see we build a right triangle, ABC, where the line segment AB actually lies on our line.
Okay.
And so the side length B is just given by x2 minus x1. The side length A is given by y2 minus y1. And so we note that we actually get out our typical slope formula of y2 minus y1 divided by x2 minus x1 by taking the ratio of the lengths of the vertical and horizontal lines.
Ah, yeah.
So this is something we can play with. We take a line, we build a right triangle that has its hypotenuse on the line, and then what we do is we can take the ratio of the vertical and horizontal sides, and this is going to give us the slope. Nice. So this is a key and sort of like really fun and useful concept. We take a line, we make a triangle where its 2 sides are horizontal and vertical, its hypotenuse is on the line, and we're going to take the ratio of the lengths of the vertical and horizontal sides, and we get the slope. And by using this geometric formulation, we can actually get some cool properties about slope out from using things we know. So for instance, I'm going to argue that by using a translation, we can actually see that these right triangles that I've described, corresponding to any two parallel lines, that these are similar. And so parallel lines are going to have the same slope. And we're going to look at this visually. Curtis, do you have something for me?
Yeah, I think I do. I think I do. So based on what you've just told me right here,
Okay.
if I can prove that triangle ABC that I've got labeled here, and you can see it on my screen,
Mm-hmm.
is similar to this triangle here, right?
Mm-hmm.
If I can prove that this triangle ABC is similar to that triangle here, then I should be able to say without a doubt that this line is parallel to that one. Is that kind of what you were talking about?
That's exactly what I'm saying.
Okay.
Showing that
So
the slopes are the same.
So I'm going to work on
to,
trying to come up with a way that these two triangles, like being able to prove these two triangles are similar. So
Okay.
from the past, I learned something from you in all of this that I think it's, it's a really good idea. I can actually just take this, this triangle ABC.
Mm-hmm.
I'm going to take point C. Actually, I'm going to take the whole triangle. And I'm going to map it right here to this new point C prime so that it maps up right on top of the one that I had before.
Right, you're just doing a translation. You're just
so that's a rigid
piece
translation, rigid transformation that maps it to here. And now I have this A prime, B prime, C prime that I've got these two guys together. Now I've got this larger triangle, and I'm going to try to make sure that this smaller triangle is in fact similar to that larger one. And the way I do that is by, well, now I've got a dilation that I can probably apply, right?
Mm-hmm.
I apply a dilation. So let's do that. Let's get this triangle.
Yeah, our fixed point should be
about that point.
Yeah.
About this point right here. And I'm gonna, it looks like it's about twice, right? So this is 3 and now that's 6. Mm-hmm. So I'm gonna say it's by a factor of 2. And if I map that, now you can see Perfect. Now you can see my second triangle, A double prime, B double prime, C double prime, is in fact right on top of that other slope triangle that I already had drawn there. So there is a set of rigid transformation plus a dilation that will map this triangle to that one. So I'm thinking that these two lines are in fact parallel. You want to see for sure?
Yeah, let's see.
Let's actually see for sure. So if I show the equations for F1, which is the blue one, and F2, which is the red one here, I can see the slopes of my two lines being equivalent. Now, my intercepts are different, but notice what I have here. If I think about this equation as y equals mx plus b, the m portion, this factor in front of x, is the same in both of these equations. I have 1/2 and 1/2. So
exactly.
I have parallel lines.
Right. So first of all, we can see that these are parallel because we get from one line to the other by a translation.
True.
And then the key thing is because we showed these two triangles are similar, we know that all the side lengths of the triangles are just some fixed scaling of each other. And so when we take the ratio of any two, the scaling doesn't matter.
Right.
So that's how we know that the slope is going to be exactly the same for both of these lines. And so we know that parallel lines have the same slope.
Nice.
All right, now let's see what else we can try to show. So,
all right. So why don't you start sharing your screen?
I did, where I'm ready to go. And so now, if we try to use a rotation, maybe we can do something with perpendicular lines. And I argue that if two lines are perpendicular, meaning they intersect and they form a 90-degree angle, I think that the slopes of those two lines are negative inverse of each other. So if one line has slope m, I think the second line has slope -1/m.
Okay. Okay. So John, do you want to, okay, so I've got an exploration here that we can see. I have two lines here that I'll propose that they're perpendicular. They sort of look that way. I can almost imagine a 90-degree angle in here.
We aren't going to do view angle, but we can trust you that these are perpendicular.
Well, okay, so I could measure the angle, but the point of this is not to necessarily go that route. What I think we ought to do is go ahead and follow your instructions, and let's map triangle ABC onto this smaller triangle over here, using a rigid transformation, a dilation, and now if we add in the rotation, 90 degrees, we should be able to prove that these two in fact are perpendicular. What do you think?
Yeah, although I do think that, how should I put this? One way that you could show that these two things are perpendicular is just by rotating one 90 degrees and seeing
Absolutely.
if one line lies on top of the other. Once we sort of see that these two lines are perpendicular, the cool thing is the similarity part is going to prove that these two things have they have the negative inverse slope. So first we can verify they're perpendicular if you want, just by our first step.
Oh, sure.
Okay.
Yeah, we can definitely prove that they are. We can definitely prove that. I need to have though on top of each of those. So I'll put that on here. So let me do that. I'm going to put a line on top of this one. Okay, so I'll just grab a point here. So we've got that point. So I'm going to make 2 lines. Okay, and this one and that one. And I'll do a rotation of this one and just see that it maps it right on top of this other line that I've got here.
Okay, cool.
So let's do that first.
Okay.
So this line, I'm going to rotate it about that intersection point.
Yep.
Okay, because I think that's important. We're going to rotate about that intersection point. Okay, and then I said 90 degrees. So let's see if when I rotate that about that 90 degrees, oops, I saw it pop up down there on the bottom corner. It did in fact line up right on top of this. So we definitely see that those two guys,
they're perpendicular. So we definitely know that for sure now.
Right. So
and so
down here in the corner.
Nice.
About that. Rotated about that. So now we can see that line. There we go. Now we see them. Right. So we're all there. Definitely.
Nice. And now that we know they're perpendicular, we're going to want to show that these two triangles are similar. And then by showing that they're similar, we're going to be able to show that these two perpendicular lines have negative inverse slope of each other.
Nice.
Okay.
So let's try getting this triangle ABC to this little piece here. So using some of your other strategies that I've had you do before, what I'm going to do is I'm going to try translation first.
Perfect.
I'm going to take this point A.
Yeah.
And noting that that's kind of the right angle of my triangle, I'm going to map him over here to this point.
Okay.
Fair? I'm going to map it to there.
Sounds good.
I did the wrong thing. Let me try that again.
Take your time.
That point, and we're going to try this translation. I'm going to take point A. I'm going to take that polygon, and I'm going to map him right here.
Perfect.
I'm going to just get that. That's my first piece.
All right. It looks like we might need a little bit of a rotation now.
Yeah, let's apply a rotation.
Yeah, maybe like clockwise 90 degrees.
So we can do clockwise 90 degrees. In order to do clockwise 90 degrees,
same as counterclockwise 270 degrees.
I can either do counterclockwise 270 degrees, or I can put in a negative.
So you can do negative 90 degrees.
So we could also do that negative 90 to get it to rotate.
Yeah, let's do negative 90. It's intuitive.
Okay. So I'll type in negative 90. Oops, I'm going to put in a negative in front of that. Negative 90.
Okay.
Okay, and so now I've got that.
Perfect.
In there.
And now it looks like we have a point that's on top of itself. It looks like one is a bigger version of the other, and it looks like we just need to scale it down by a factor of 1/2 is what it's looking like.
Looks like we probably can do a dilation on that figure about that point. And you said 1 divided by 2, 1/2.
Yeah, 1/2.
All right, so I'm going to just pop that in there. And so A triple prime, B triple prime, C triple prime should line up right on top of our other.
Perfect. And they do.
This has gotten a little bit crowded, so I'm going to hide a few things.
Okay, perfect.
Get some stuff out of our way so we don't have
Good.
Oops. I think I still need to hide one more. Let me hide this this bigger triangle.
Okay.
This guy. No, I don't want to hide the label. I'm going to hide this whole. Come on. I want to hide everybody.
Okay.
Let me hit tab and I'll get it. There we go. That's what I wanted.
Yeah, just yeah. Okay, perfect. Hide some of those points, and now let's talk through, now that we've seen that these two things are similar, let's talk about what this means in terms of the slopes. So we can see that the horizontal line for triangle ABC becomes the vertical line for triangle A triple prime, B triple prime, and C triple prime. And the vertical line for AC becomes the horizontal line for A triple prime and C triple prime. And so what this tells us is that the slope formula for this red line, we're actually flipping the x length and the y length, so that now for the blue line, the slope is the length of AC over the length of AB. Once we change to the perpendicular line, now what we want is the length of A triple prime, B triple prime, divided by the length of A triple prime and C triple prime. The one thing to keep in mind, though, is that this red line, when we do this transformation, we see that we're actually moving up in the y direction, but we're now moving left in the x direction.
Yeah.
So when it was positive before, now we've gotten a negative term, and we flipped the ratio that we had for the blue line. And so the flipping is how you get the inverse. And the fact that now in the x direction, we're going to the left rather than to the right is how we get the negative. And Curtis, it looks like you've shown us the formulas for these lines. And what do we see when we look at the algebraic equations?
Well, if I look at this equation, I had an original equation, this f1 of x, has a slope of positive 1/2, right?
Mm-hmm.
So in order to talk about both that reflection, that inverse, and then taking the negative or showing the opposite value, I'm going to get 2/1, and I'm going to get the opposite value, which is the negative, right? So my slope on this red line is in fact the opposite reciprocal of that slope of that blue line. So we do in fact have those two things. And so your proposal earlier that if two lines were in fact perpendicular, that the slopes would match up as 1/2 and -1, and -2.
Negative inverses of each other. It seems like this is true. And we showed this using similarity, which is sort of kind of cool. I don't know.
I think this is really a neat one. Sorry, I kind of didn't clean up all the labels there.
No, it's okay. I mean,
got a little messy on us, but
you're working with some sort of heavy duty machinery. But the main take home is that, I don't know, we've during these 5 sessions, we've really had a chance to sort of dig into sort of congruence and similarity in a sort of much more rigorous way. And then it's been nice this last session to sort of use these things that we've learned to try to connect some sort of things that sort of might have felt like different areas of math before this session, and show how they're related.
Yes, the interconnectivity between these two topics and really just this whole strand of things actually is super cool. And I love how we were able to use congruence and similarity to prove some things algebraically, and then reversed it, put it on its head, and said, well, we're going to do a little bit of algebraic manipulation to prove some congruence and similarity. So we really did that in both directions and saw the connection between the two. And so that was really great. So John, I've certainly enjoyed making these sessions with you. It's been a lot of fun. But I guess this is the end of the Smart Space Geometry video series. So we'll see you around.
Yeah, no, thanks for having me. And I hope you guys really enjoyed these sessions.
Yeah.
You guys have a good one. Okay.
All right. Take care.
All right. Bye.